This lecture topic is on something that is probably the most familiar to you out of anything, the idea of correlation and regression. And we'll keep it specifically to linear things, but um, this is something that uh, I would imagine most students have some sort of grasp of, but probably not in the calculations, yes, but probably in the actual deeper meaning of what certain uh, parameters or calculations are, maybe not. So we're going to go through and hopefully give you a better appreciation of what things like a correlation coefficient mean. And so the first thing we're going to go over is linear correlation. We're going to define a correlation coefficient as a coefficient that measures the strength of association between two variables. And so um, you might then, might be not too big of a leap to imagine that there would be one that would measure the strength of linear association between two variables, and there is. It's called the Pearson product moment correlation coefficient. Instead of saying PPMCC for short, we're just going to define it as a little r. And it has the following properties. It ranges from -1 to 1, and the greater the absolute value of r, the stronger the linear association. So to have if an x and a y variable have an association of 1, it means that they're as strongly linearly associated as possible. And if they have an association of -1, it means the same thing. The strength of the linear association is the same. The weakest linear relationship is actually 0, so it lies in between, which would mean that there's no linear association between the two. So a positive r value means that the dependent variable y would increase as the independent variable x increases. So the value of 1 or -1 gives you both a strength and an association with it. So positive slope between y and x would denote a positive r. Negative r means that the dependent variable decreases as the independent variable increases. So something with a negative slope, for example. And we'll use this in understanding linear regression a little more. What we'll use for regression is what's called least squares regression. And this allows for the prediction of a dependent variable y based upon an independent variable x. And the prerequisites for that are that y has a linear relationship to x, which you could test by finding your little r value, or through what's also known as residual analysis, which we'll cover in a minute. And so least squares regression, it calculates a predicted line y hat as a function of x. And so you'll have y hat, which is your predicted line, and y, which is your actual dependent values. And it takes the form of y hat. If it's a least squares linear regression, it's just a line. Y hat is equal to what we call b0, which is basically the y-intercept, the calculated y-intercept, plus b1, which is a calculated slope, times x. So what least squares regression does is it creates an equation y hat that minimizes the sum of square differences between your observed values of y and your predicted values of y hat. So this is the equation for finding the slope of your least squares regression line, and it looks a little hairy with the summations and whatnot in the numerator and denominator, but it can be simplified as to the numerator being r, which we can find, which is just the little r that we talked about, the linear correlation coefficient, multiplied by the standard deviation of your dependent variable, or your y. And then your denominator is just the standard deviation of your independent variable x. And this is actually the equation for r. It also looks a little hairy, but you know, the point of this lecture is not so much to ingrain in you doing, you know, rote calculations so much as the meaning behind them, because any program such as Excel or MATLAB can do this pretty much in the blink of an eye. So it's more an understanding what linear correlation and what least squares regression is actually doing to help you in the future. But to give you an appreciation, we still show them. And your calculated y-intercept is just going to be your mean y value minus your calculated slope times your mean x value. So along with the linear correlation coefficient, there's also what's called a coefficient of determination, which is, we denote as big R squared. And it's the proportion of variance in y that can be predicted from x. So it's another measure of how well independent and dependent variable are associated. Just you know, it's different, but it's not necessarily linear association like little r. Interestingly enough, though, the coefficient of determination is just the linear correlation coefficient squared. And so its properties are, it ranges anywhere from 0 to 1. It can't take a negative value since it's a squared, with 0 being having where no variation in y can be predicted from x, and 1 being that everything, all the variation in y can be predicted from x. And so another topic we're going to cover here is what's called residual analysis. Now, it was mentioned earlier as a method for trying to see the strength of linear association between two variables just through visual inspection. So residual is the difference between an observed value of a dependent variable and the predicted value, so whatever the difference is between y and y hat. And as you'll recall, this can be related to a least squares regression, in that the whole process of a least squares regression is to minimize this difference, or this residual value. So E, which is the value, or the sign we'll associate to a residual, is just y minus y hat. And it takes the properties of, has the following properties. Within a given data set, the sum of all the residuals and the mean of the residuals is always equal to 0. And in general, a random pattern centered around a residual line of E equals 0 suggests a good fit for linear association. So what you can see on the left is what would be considered a good linear fit between an x and a y. E equals 0 is let me use my pen, see if I can make a straight line. Not really, but you get the idea. So E equals 0 runs right here, and all the data points kind of are randomly scattered around E equals 0. Whereas here, you can see that there actually is a pattern to the residuals. It has a parabolic shape to it, which I try to draw here. Whoa. So not that great of a parabola, but again, you get the idea. So that would not be suggestive of a good linear fit between x and y. So residual analysis is a great tool to just quickly check and see how well things are could be fit to a linear curve. You can actually even do hypothesis testing for regression slopes to see if there's a statistically significant linear relationship between x and y. And so starting at a null hypothesis, your null hypothesis would be that your calculated slope in your least squares regression line B1 is equal to 0. And your alternate would be that it's not equal to 0. And the t-statistic just follows, it's the calculated slope over standard error, where the standard error is this value right here. You'll know your y value because that's your measured value. This is your, this is your observed y value. This is your predicted y value, and your observed independent x, and the mean of that. And the degrees of freedom in this case is not n minus 1 like it was for doing a mean, but n minus 2, which is important to note for doing the analysis. And so, so we're going to talk about transformations and outliers. And the first thing we need to do when I mean, everybody talks about statistical outliers, but nobody actually, but I doubt that many people actually know what the real definition is. And they're actually data points that diverge from the overall pattern of the set, which would seem intuitive, but so there's actually 4 different types of outliers that you can have in your data set. So if this is a given data set, just these little blue circles here, the first is that there can be an extreme x value, which would show up somewhere over here, right here. The next is you can have an extreme y value here, extreme x and y value, which puts it above the data set, and then what is generally called a distant point, or a value that isn't extreme in any one case, but definitely looks like it doesn't belong. And this, you know, you don't want to be too liberal with identifying outliers, but it's worth noting, you know, when you do a scatter plot of your data, what could be an outlier and what just doesn't make sense at all. And so, along with outliers, we'd like to look at transformations, because if your raw data doesn't appear linear, you might be able to transform it in a way that the transformed data does look linear for doing things like least squares regression. And so there's 2 types of transformations. There are linear transformations, which basically don't change the correlation between x and y. You either multiply a variable by a constant or add a constant. Or what's more commonly used is a nonlinear transformation, such as a logarithmic transformation. You could, taking exponentials of data, square roots, and along with others such as reciprocals, or and once you take the once you transform your data with one of these nonlinear operators, you can test the linearity of your transformed data through residual analysis. So you can still use that on your transformed data to see how well how linear your new transformed data set is. So here's an example of what we're talking about. Obviously, this is some idealized data on the left, and you can see that it's obviously nonlinear in its shape, and you know, it does look like some form of exponential growth. So we'll just assume that it's some, you know, e to the x value. So we say that y is equal to e to the ax plus b. Okay. Now, when we transform that by taking the natural log of each side, which is one form of a nonlinear operator, we take the natural log of the left side and the natural log of the right side, we now have a linear set of data. So x is linearly related not to y, but to the natural log of y. And so then we can go through and do least squares regression and those types of things.